In this section of the earthquakes chapter, we'll take a closer look at what can happen to structures from ground motion and also learn about measuring earthquakes. So most buildings are designed to hold up pretty well to vertical motion because of the weight of the building, because the stuff that's in the building due to gravity. So vertical shaking in earthquakes is usually safe. Now, that's usually safe. California seismic code has foundations that have to be overbuilt. Well, overbuilt would consider to be overbuilt in some areas of the country, most areas of the country, to handle vertical shaking. But the one that we're going to concentrate on today is horizontal shaking, because the horizontal shaking in earthquakes can do great damage to buildings. And the reason for this is something called resonance. All buildings have a natural period or resonance. That is the number of seconds it takes for a building to naturally vibrate back and forth. All buildings move back and forth. Again, that is called resonance. If the period of the love wave moving underneath a building matches the resonance of the building itself, then that back and forth movement is increased and the building can fail. So these oscillations, back and forth oscillations, can do grave, grave damage to total destruction to these buildings. And this is what we're talking about. Again, a shorter building will have a shorter period of resonance. A taller building is more flexible. It's going to have a longer period of resonance. For example, a 5-story building might have a resonance of a half a second, while a 50-story building would have a resonance of 5 seconds. So you can kind of get the idea here of what happens if you have buildings adjacent to each other that have different resonance. They can actually collide with each other during an earthquake. This is Mexico City, an earthquake that occurred there in 1985. It was an 8.1 magnitude quake, and over 412 buildings collapsed due to resonance. Many of these were 20-story buildings that have, and a 20-story building would have a natural resonance of 2 seconds. It turns out that that coincided with the resonance of the love wave moving underneath. So you had all of these buildings that were destroyed. There were about 5,000 people that were killed during that earthquake. Here's another example of a building that was destroyed during that particular earthquake. So I've put these links in here to 2 YouTube videos that you can look at. They're pretty interesting. They're in Japan during the 2011 Tohoku earthquake, which was a 9.1. And these videos perfectly illustrate the movement of these buildings. It's really scary to watch these tall, huge buildings just swaying back and forth like nothing. But if there's any country prepared for that, it's Japan. They are really good at the seismic codes that they have, and they have these construction techniques that they use for buildings. There's one in particular, if you watch the video, where there are 2 buildings next to each other, and they have this structure that's built between them. It's a walkway, but this structure will move in and out of itself as the buildings are moving back and forth. So I hope you take a look at these. So what are some of the things that, some of the techniques that we can use to keep buildings safe during earthquakes? Well, we frame the buildings in different ways, and then of course if the building is older and it's not built to any kind of code, we can retrofit the buildings. Some of the techniques that are used are cross bracing, and you see that in the picture on the left here. Let me grab one little laser pointer. You see the cross bracing here, so the structural integrity of the building is increased as a result of that. We can also use a technique called infilling. I'll show you an example of that. Framing it, so that it's more structurally sound, we can buttress it, and we can also isolate it. That is called base isolation. So in earthquake country, we have to build shear walls. Shear walls are designed to take the horizontal forces from floors, from roofs, from walls, and transmit those forces to the ground. So you see that the diagram to the left here, where we have a stack of playing cards. If those weren't reinforced, they're going to fall very easily with just a minor shake. So shear walls, you see how the cards are taped together? That's in a much more major way how shear walls work. Parking structures are particularly prone to failure in earthquakes because they lack shear walls. Well, I'm becoming kind of an expert at shear walls because we are in the middle of building an addition to our house, and with the California requirements for seismic building codes, it gets quite a kind of crazy. So these are some pictures from that construction. The metal building that you, or not building, but the metal part of the wall right here that you see, that's a shear wall. Then this picture shows a wall reinforced with plywood and also braced. And the nails are very close together. I didn't include a picture of how closely spaced the nails are, but on the other side of that wall, this is what it looks like. Again, this bracing between all of these boards. I'm not sure what the technical term for these are, but you have bracing between them. So all these things together add up to a building that can withstand not only the vertical shaking that might be associated with an earthquake because of the foundation that we had to build, but the horizontal shaking from an earthquake. This picture, not my house thankfully, but this shows the buttressing technique that stabilizes a structure during ground motion. And then this one is an example of infilling. The concrete frame has been infilled with clay bricks to make the building more structurally sound in the event that there is an earthquake. And this picture shows a bridge column that didn't hold up very well in an earthquake. And we thought that this was the way to go, reinforced concrete. But several earthquakes here in California, specifically the San Fernando earthquake, illustrated that we're not building things properly when there's this amount of shaking that can take place. So that's reinforced concrete, and that's good. We always want reinforced concrete, but you see what happened. The steel failed and the concrete crumbled. So what we've learned is to do it a different way. We layer these materials. We still have reinforced concrete, but look how much closer these steel bars are together than these were. They're closer together and they're wrapped. And again, this is concrete here inside, and then the concrete itself is wrapped in these steel plates. So the steel is ductile, it's able to bend. The reinforced rebar in the concrete will keep the concrete in place during shaking. So that's the new way of doing things. And this is kind of the ultimate. This is the best technique of all, but it's very, very, very expensive. This is called base isolation. What you're looking at in the little inset picture down here, that's the Google office building in Cupertino. And they, of course, this is a seismically active area, so being Apple, they're gonna have the Rolls Royce of everything. So this building has 700 of these base isolators. And what they are, as I said, they're 7 feet in diameter. They weigh 15,000 pounds each, and there are 700 of them. So these things are installed between the foundation and the structure of the building, and they're kind of like these huge shock absorbers, and that takes the brunt of the movement. The energy is expended in these things rather than in the building itself. Japan has over 4,100 buildings that are base isolation. Japan is a country that really depends on the base isolation system for their buildings. That's why if you watch that video, you see that the buildings are swaying back and forth, but they're not cracking. You hear rumbling and kind of creaking sounds, but the integrity of the building isn't impacted in any way. Turkey is also a country that is employing a lot of these base isolators for hospitals and bridges. China, New Zealand, Chile, they all use them. We in the US use them less frequently. This is one place where they're used. The what's it called? The county building, the city hall in San Francisco. It was retrofitted to be to have base isolators underneath. So again, this is the Rolls Royce of techniques to use in earthquake country. All right, so how then do we measure earthquakes? There are two measurements in an earthquake. There's the magnitude of the earthquake and there's the intensity of the earthquake. These are two different measurements. The magnitude measures the energy released at the source of the earthquake, and an earthquake will only ever have one magnitude. Intensity measures the strength of the shaking produced by an earthquake at a certain location. It's a descriptive measure, whereas the magnitude is a quantitative measure. And there can be different intensities in different locations, different people, different structures, different foundation, different geology. Everybody can feel something different. And for the modified Mercalli scale, which is the intensity scale, we measure those in numbers, Roman numerals from 1 to 12, with 1 being not too much happened, 12 being total destruction of an area. So I'm going to start by describing how the Richter scale works, but keep in mind that this is not the scale used nowadays. The one we use is called the moment magnitude, and it works the same, but there's more to it. It's a modified Richter scale, and it measures the amount of fault slippage and rupture. So theoretically, with the Richter scale, you would never have to go out of an office or a research facility to know what the magnitude of the earthquake was. But again, this got redone. So I'm going to tell you how the Richter scale works. Bear with me. Charles Richter was a seismologist at Caltech, and he wanted to have a way to compare the energy released in an earthquake and the amplitude of the surface wave. He wanted to have a way to compare those for earthquakes that occur in California. So he's down at Caltech with a bunch of astronomers, and they already have a star magnitude scale that they use. So he kind of took a page out of their books and said, well, hey, I'm going to do the same thing and just modify it for what I'm doing. So let's go over here. I need to quit saying so. So I will. Theoretically, there should never be an earthquake that has a magnitude of over 10. And you'll see why in a second. Let me grab a little pen here. And there are two things that we can do with this scale. We can measure the difference in wave height between earthquakes, and by wave height, it's the surface wave that we need that will tell us what the magnitude of the earthquake is. Specifically, it's the highest surface wave that is measured at a seismograph. So for that, I'm just going to abbreviate that wave height. For that, the magnitude of difference between each whole number is 10. And I won't do a 10 all the way through here. You get my gist of what's going on. I'll do one more 10 between 4 and 5. All right, let's say that we are comparing the wave height that has been measured at a seismic monitor, and we want to look at the difference in that between an earthquake with a magnitude of 5 and an earthquake with a magnitude of, well, let's say 2. We're not going to feel that, but so you see that there are 3 magnitudes of difference here. 10, 10, 10. 5 minus 2 is 3, so 3 magnitudes of difference. What do we do with those 10s? This is a log scale. So we are not adding these numbers, we are multiplying them. So 10 times 10 times 10 equals all day, every day, 1. So the wave height at an earthquake with a magnitude of 5 would be 1,000 times higher than an earthquake with a magnitude of 2. That's wave height. The second thing that we can do with these numbers is we can compare the energy. I need a whiteboard. Maybe if this goes on very much longer, I'll learn how to use a whiteboard. The energy released. Energy released. And that's supposed to be a D. And we don't use 10 anymore. The number is 30. It's actually 32, but for ease of multiplication, I'm just going to use 30. 30 times 30 times 30 is equal to, well, what's 30 times 30? 30 times 30 is 900, and 900 times 30 is 27,000. So let me really do some math here. that's 900. Oh, 900 times 30 is equal to 27,000. Now think of that number. There's not, if we're just doing a numerical scale, there's not that much difference. There's, 2 and a 5. Well, those seem fairly close together, but this is a log scale, so these numbers go up exponentially. 10 to the third, 30 to the third. An earthquake with a magnitude of 5 releases 27,000 times more energy than an earthquake with a magnitude of 2. Now, how do we measure energy? It can be in a variety of ways. Sometimes you see it as the amount of energy in tons of TNT, or the amount of energy that was unleashed in an atomic bomb like the size of the one dropped at Hiroshima. Sometimes you see those kind of things. So let's just say if we use that example, let's say, and I'm making up these numbers because I don't know that a 2 would release this amount of energy, but let's say a 2 releases the amount of energy in one average size atomic bomb. Then a 5 earthquake would represent 27,000 more, 27,000 of those average size atomic bombs. So we go up, up, up. This is why we never want to see a 10. Can you imagine if 3, in most circumstances, somebody will feel something. It might be nothing more than like a rumble or maybe a little shake, but usually people, especially close to the earthquake, will feel a little something. So think about the energy released in a 10. That's 30 to the 7th. I don't even know I could do it, but that's millions of times more energy released. There's nothing man-made. There's nothing, mountains would slide. Mount Rushmore would probably come crumbling down. There's nothing that could withstand a 10. The highest magnitude earthquake that we've ever had, ever recorded since record keeping began, was in Chile. I think it was 1960, and it was a 9.5 magnitude earthquake. So that's how this scale works then. We're comparing the wave height, and if we're comparing wave height, we use 10, and we can compare the energy released, and if we're comparing the energy released, then the number between each whole number is going to be 30. All right, so let's look at this. Here's we start with a 5. 5 is our base, so it's going to be 10 to the 0 here, which equals 1. And then remember, I'm going to use 30 on any testing that I do, but 32 to the 0 would be 1. In here, we would have 10. Oh boy, here I have to start this again. 10 to the 1st and 30 to the 1st. To the 1st. That looks like 4, but it's supposed to be 1. So that equals 30, and this equals 10. So wave amplitude, difference in wave height. Amplitude is just a fancy word meaning height. Then if still 5 is what we're comparing it to, then we're going to have 10 to the 2nd here. That's 100. Here, 10 to the 3rd. So an 8 would be, the wave height would be 1,000 times higher than with a 5. And then 30 to the 3rd here, again, that's that number, 27,000 times more energy released in an 8 than in a 5. If you have any questions about this, all you have to do is shoot me an email. So expecting the big one. Sometimes you hear people say that because an area has experienced a lot of little earthquakes, then maybe that those stresses are being released and we won't have the big one. Let's see how that pans out. How many magnitude 6 earthquakes would it take to release the same energy as one magnitude 8 earthquake? Well, we're looking at a 6 and we're looking at an 8, right? So the difference between an 8 and a 6 is 2. What is the number that we're going to use? It's going to be 30. I think in this example they use 32, but that's going to be 30 squared or 32 squared. So how many magnitude 6 earthquakes would we need to release the same amount of energy as one magnitude 8? The answer is about 1,000. I think it turns out to be 1,024 or something like that. In Southern California, the historical records indicate one magnitude 8 earthquake every 160 years. The last magnitude 8 earthquake was in 1857 near Fort Tejon. Well, if it was 1857 and the records show that we can expect one every 160 years, then the date of the next one is 2017. Well, we've gone past that date. Have the regular magnitude 6 earthquakes released the stress along that portion of the San Andreas? Therefore, we don't have to worry about a magnitude 8? Well, let's see. It would take 1,024 magnitude 6s to release the same energy as one magnitude 8. That's equivalent to 6.3 magnitude 6s each year. How did we get that? 1,024 earthquakes, the number we need, divided by 160. That comes out to 6.3 earthquakes per year. Our next question is, have we had that many? No, we have not. we've historically experienced a magnitude 6 earthquake about every 4 to 5 years. So the stresses are still there, the stresses are still building up, so we can still expect a magnitude 8 coming soon. This is a surface rupture from a 6.4 moment magnitude that occurred near Ridgecrest, California in July. That was a 6.7. 6.7. I thought I read that somewhere, but this says 6.4. So when I wrote that, I'm sure I was correct. So I'm going to go with 6.4. This is where I got 7.1. The next day, that 6.4 turned out to be a foreshock. The next day, there was a 7.1 moment magnitude earthquake. 3.5 feet lateral offset. Look at the road here. This is near China Lake. This is a service road into the naval base there, or the weapons depot, whatever it's called. China Lake. That's the road being displaced. So that was movement that occurred. And just generally so you know, some of these magnitudes, 3.0 to 3.9 felt by some, 4.0, 4.9 felt by most, 5.0 to 5.9 can have damaging shocks. 6.0 to 6.9 is considered to be a strong earthquake. 7.0 to 7.9 is a major quake. And then greater than 8 is great, devastating, destroys things near the epicenter of the quake. Now, if you think about magnitude and intensity, can you think of any examples where you could have a high magnitude earthquake but a low Mercalli intensity? I'll let you think about that for a second. What about, and I'm sure some people thought about this, what about non-populated areas? What if you have a high magnitude quake under areas where you don't have a lot of structures? If you don't have a lot of structures to be damaged, which is what the intensity scale deals with, then you're not going to have a high Mercalli intensity. No highways, no buildings. But then you could have a low magnitude earthquake and get major damages. And that can happen in areas where the structures aren't built in a good way. They don't have the economic wherewithal to retrofit things or to build them to withstand earthquakes to begin with. So you can have both of those scenarios going on. And again, the modified Mercalli will go up to 12 in Roman numerals. And you can read through these. I just gave a few examples. So somebody has to go out. You have to have boots on the ground here. Somebody has to go out and interview people. They have to survey the damages. What was damaged? Was it wooden structures? Was it reinforced concrete, unreinforced concrete? How about bridges? How did they hold up? All these things have to be taken into account. Normally, it will get a 5 if they interview people and they say, I was asleep and the shaking caused me to wake up. It will get at least a 5 then. All right, that brings us to secondary effects of earthquakes, and I'm going to save this for next time. So I will see you later.